This is delta X.1. We are going over function analysis. I did a practice test earlier today, and I just noticed how many of the problems had to do with function analysis. Really, nearly 33% of the questions, a third of the questions have to do with function analysis. Not necessarily like all in the same way, like these problems, but understanding what does it mean for a derivative to be positive? What does it mean for a second derivative to be positive? This is so important. And as we're getting towards the test, it's really important to be sharp on this coming up. You'll thank me later. So if you're here, you're one of my favorites. If you're watching this video, one of my favorites. Okay. We're going to start with a little bit of review, and feel free to do this on another sheet of paper if you need more space. But I'm going to talk a little bit again about, the function, the first derivative, and the second derivative, and what that means. And I'm going to write as neatly as I possibly can. This is going to be my neatest work. So we have um, f of x, which is the function. We have the first derivative, that's f prime of x, and then we have the second derivative, that's f double prime of x. And I'm assuming you're good on that notation, and I don't need to explain that any further than that. You know that. Um, if the function is increasing, let's do this together, guys. Let's do this together. Okay, you tell me. If the function is increasing, that means the derivative is positive. That's right. The derivative is positive. What does that mean about second derivative? We don't care. It's not applicable for this row. Okay. All right. That's the first one. Second one we've got is, what do you think is next? Decreasing. Let me try not to cover everything up. Decreasing. Right? If the function is decreasing, that means that the derivative is what? That's right. Negative. Okay. And we don't care about the second derivative. Okay. If we have a relative maximum, what does that mean about the first derivative? Tell me. That means it's doing, what is it doing? It's changing. Look, it's going changing from increasing, right, to decreasing. That's a relative maxima, right? So that means that the derivative must be changing from positive to negative. Remember, derivative is slope. So if I'm changing from positive to negative, I must have relative maximum. Okay, I'm going from increasing to decreasing. Positive slope to negative slope. What about my second derivative? This is where it comes in. Look at this shape right here. What is this? What concavity is that? Right? That's right. It's concave down. So that means my second derivative must be negative. It must be the second derivative must be negative. Okay? Relative min. Can you do this when you're by yourself? Test yourself, guys. If you're watching the video, you know this. If that's positive negative, relative min would be going from negative decreasing to increasing, right? So it's going to go negative to positive, right? And so same thing. Look at that concavity. What's the concavity of this? That's the relative minimum, right? What's the concavity of that? Concave up. So that means the second derivative must be positive. Last thing I want to cover here is critical point. So critical point means it includes a relative min and relative max, but it's also just simply where the derivative equals, you know it, that's right, 0. Or it can be undefined. What that means is that it would be a 0 in the denominator. If you had a 0 in the denominator, that would be undefined. Okay. Um, I'm gonna add that. The denominator is 0. That's what that means. Okay. And what about the second derivative? Yeah, this is not applicable here. So a second derivative only tells us about like relative min and relative max. Um, it can tell us if a critical point is a relative min or a relative max, but a critical point itself, it doesn't help us with that. Does that make sense? So if you find the critical points and then you find that the second derivative is positive, you know it's relative min. Or if it's negative, you know it's relative max, but it doesn't help us specifically with critical points. Okay, let's do the other side of things. So we also have, I'm just saying kind of chart over here, but for the second derivative, we have the function, we have the first derivative, and we have the second derivative. So if the first derivative is concave up, that means, did I say a derivative there? If the function is concave up, that means the first derivative is increasing. The slope is getting steeper. That means the second derivative must be positive. Okay? If it is concave down, that means that my slopes are decreasing, which means that my second derivative must be negative. And just to remind you about that, in case you're like confused about that, why is this concave down? Because if you think about this, my pen is the slope. I start very, very steep. I'm getting shallower, I'm getting shallower, I'm getting shallower. I'm at 0, and then I go negative. That's concave down. It's always decreasing. My slope's always it's always going down. Versus when it's concave up, I start very steep down. I'm getting less negative, less negative, less negative, less negative, 0, positive, positive, steeper, 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 right? And so on. So just a good reminder. That's concave down. Slopes are decreasing, more negative. Okay. The only other point here is inflection point. And an inflection point happens when the first derivative has what? When the first derivative has extrema, has an extrema. That means relative min or relative max, right? Okay. And that means when that's happening, if I'm having a relative min or max here, that means that my second derivative must be changing signs. It must be changing signs. It's not enough for it just to equal 0. It must change signs. Okay. So when we think about the AP test, you think about your readiness for the AP test. Can you tell me this from scratch? If I say that the function is increasing, can you tell me the derivative must be positive? If I say it's an inflection point, do you know that it's an extrema in the first derivative, and do you know that the second derivative must be changing signs? And then do you know how to apply that? That is what the AP test asks of you. And those are the kind of problems we're about to try. It's so important, guys. It's so, so important. It's so much of the test, including one of the entire FRQ problems is just this, right? So you just got to know it. You just got to know it. Let's do some practice problems. So this will be familiar to you. You'll remember this. Some of these are from, they might have been from that dreaded Delta 2.5, I think it was. I can't remember which one. There was one that was dreaded by everybody. Here we go. So given a function f of x equals the integral from negative 2 to x, t to the third minus 12t squared, determine all the intervals where f is increasing. So something interesting with this one is this is a callback to my first video on fundamental theorem calculus part 1, and I talked about how this is very relevant for these kinds of problems because you have to know that the derivative of an integral from some constant to x is just what's inside, it's just a function that's inside. So in this case, you wouldn't freak out. You'd say, okay, well what do I have to do here? I want to know where f is increasing. That means I want to know where the derivative is positive. I want to know where that's happening. So that means I have to find the derivative. Okay, so I need the derivative of x. And this is the fundamental theorem of calculus part 1, is that the derivative of an integral from a constant to a variable is just the inside. So the derivative is just x to the third minus 12x squared. And then from here, you're going to set that equal to 0. And then you do your sign chart, the number line, right? So let's factor out the greatest common factor is x squared. So it's x squared parentheses x minus 12 equals 0. So my solutions are x equals 0 and x equals 12. Number line it 0, 12. And we test the points. This is going to be positive. Um, Plug in a 10, you get negative, and a positive is going to be negative. Plug in a like, -3, you're going to get negative, and positive is going to be negative, right? So where is it increasing? It's increasing from, I'm going to write the sentence as I would write it on an AP test. If this is an FRQ, this is how I would write it. F is increasing on 12 to infinity because the derivative is positive on 12 to infinity. I'd write something on those lines, right? If there's an AP test, f is increasing on 12 to infinity because the derivative is positive on 12 to infinity. Easy, right? This is not proof alone. You would on an FRQ you would have to say that sentence. Okay. 30. Maxima. Where do we want to find the relative maxima? So you got to know it, right? Relative maxima happen when the derivative changes from positive to negative. So you do a very similar thing with a number line, right? So we need to get the derivative. This one is not integral. It's just more straightforward. It's going to be, the derivative is 6x squared plus 42x plus 60. You're going to take out the greatest common factor, which is a 6. So 6x squared plus 7x plus 10. My factors are x plus 2, x plus 5. So my solutions would be -5 and -2. Test the points, positive. Plug in like a -3. We're gonna get negative for sure, and then we're gonna get another positive. So I would say, okay, my relative maximum must be here at -5. That's my relative maximum because I'm going from positive to negative at that point. Okay, so that would be like the pretty sentence you would say something along those lines. The other way that you could prove that it's -5 is through the second derivative. So I will show that just so you're aware. If you took the second derivative here, this is what Benny does when we were doing this way back when he was telling me. If you take the second derivative and you plug in our critical points into the second derivative, so you plug in -5, -5 goes in, you're going to get a negative number there. It's -60 plus 42, it's negative. So since the second derivative is negative, it must be relative maxima. And likewise, if you plug in -2 into here, you're going to get -24 plus 42, you're going to get positive. Second derivative is positive. Second derivative is positive, therefore it must be relative minimum. So you wouldn't have to test the points. It's like a second way that you can verify. Either you can plug in the values into the first derivative and see where it's positive or negative, or you can take these values and plug them into the second derivative, and you can like literally -5, -2 into there, and that can also tell you if it's a relative min or relative max. Okay. Keeping going here. Given the function f of x equals 3x to the third plus 27x squared plus 72x, determine all intervals on which f is both decreasing and concave down. This is a little bit more of a tough one. You have to find both the first and second derivative because you need to find both where it's decreasing and its concavity. So you need both the first and second derivative. That is going to be 9x to the squared plus 54x plus 72, and the second derivative will be 18x plus 54. Okay, and then you do two number lines. I like to do two number lines. You could do it all in one, but I think two makes it a little bit better. You got to get your solutions. So the solutions for the top one, we're going to factor out the 9 out of that. So it's going to be, let's see if we can do it really small beneath here, 9x squared plus 6x plus 8. I can see it's going to be x plus 2, x plus 4. And so it would be -4 and -2 would be my solutions there. Here I can factor this out. This would be 18x plus 3. Yes. Yep. And so my solution there would be -3. Then you test, right? So if I plug in like a 0 into my original here, you're gonna get a positive, and then I'm gonna get a negative here, and then I'm gonna get back to a positive over here, and I plug in -3 into here, plug like a 5 into this, I'm gonna definitely get a positive, and then plug in a -10, right? You're gonna get a negative. So the question is, where is it decreasing and concave down? It's within this interval, -4 to -3, the overlap of the negatives, right? Let me like highlight that for you, right? So it's, this is negative here, this is negative here. Where do they overlap? They overlap right here on this interval. That's where they're both true, right? So you'd say -4, -3, right? Okay. Last one. Okay, we're on the last problem, 46. Find all values of x for the graph of x equals -3x squared plus x times e to 3x has an inflection point. So this is similar uh, to what you've done, but difficult, more difficult. There's no difference in finding an inflection point here versus if you'd find it here. You do it the same way. You take the second derivative, right, as you would do above, and look for where it changes signs. The only difference is like it's a little bit more challenging. Like you've got something going on here, and the reason I give you this is again like the practice, because the better you get at these harder problems, the better you're going to be when the test day comes. The stronger your differentiation skills are, so many things improve, right? When you're doing this, so many things get better. So let's do it. Um, I'm going to start by just recopying it on paper because this problem is going to take some space. It's also a problem where you really want to take your time. So we have f of x equals -3x squared plus x, write really neatly like I do, right? Ha ha ha. And we're looking for the second derivative. We want the second derivative of this. So to get the second derivative, we've got to start with the first derivative. Now here, guys, I think something that's helpful for product rule, because some of you are struggling with it, is to say the expression out loud. What does this expression say? It is -3x squared plus x times e to the 3x. It is times. It's multiplication. We have a term here times another term here, right? So we must use product rule. So here we go. Lefty right plus righty left. Left. -3x squared plus x times d right 3 e to the 3x. Okay, how did I get that? The derivative of e to the 3x is just e to the 3x times the derivative of what's inside, which is 3. So it's 3 e to the 3x. Okay, plus right e to the 3x d left -6x plus 1. Okay, we're going to distribute stuff, so we kind of clean things up a bit. We're going to get -9x squared e to the 3x plus 3x e to the 3x minus 6x e to the 3x plus e to the 3x. Okay, good to just check your work, take your time. We're then going to combine these two together. We're going to write it out one more time. -9x squared e to the 3x minus 3x e to the 3x plus e to the 3x. Remember, these two terms are like terms because they both have x e to the 3x within them. Right? That is not like because it has the square. That is not like because it does not have an x. So we have three distinct terms here. Okay, very easy to make a mistake on this problem. Then, in order to avoid me doing, right, as it stands, I'm going to have to do two separate product rules right here. I would rather not. So I'm going to factor out the e to the 3x out of it and write it like this. Okay, there we go, a little bit nicer. Now it's just one product rule I have to do. Right, I just factored out the e to the 3x out of it. Okay, here we go. Lefty right plus righty left. E to the 3x. D left, D right. -18x minus 3 plus right -9x squared minus 3x plus 1 d left, that's 3 e to 3x, just like before, just like my explanation before. It's itself times the derivative of what's on the top, right? Okay, let's simplify this. So we're going to have -18x e to the 3x minus 3 e to the 3x minus 9x squared, sorry, 18x squared, because that 3 times 9, sorry, 27. 27. 3 times 9 is 27. 27. Sure that's clear. Because what I'm doing here, again, if that's not clear, the 3 times the 9 is 27. Right? X squared e to the 3x. Nearly got through without making a mistake. There we go. Had to happen. Got it out of the way. Minus 9x e to the 3x plus 3e to the 3x. Okay? So what's going to happen here is some terms are going to cancel. Notice that we have a negative 3e to the x and plus 3e to the x here. Those are going to cancel because they're just opposite terms. This term is going nowhere because it's just the same thing, negative 27. It's the only x squared term, right? So I can't combine it with anything. It's not going anywhere. And then I've got negative 18 minus 9. They're the same term, so they go together. Minus 27 uh, x e to the 3x. Final step, we're going to factor out the greatest common factor out of this, which is, as you can see, a negative 27x e to the 3x. So negative 27x e to the 3x comes out. Inside will be an x minus 1. You got to earn that extra credit, guys. You got to earn the extra credit. So what are your solutions? Well, one solution is 1 right here, right? Because that makes it 0. Remember, we want this to equal 0, right? That's the goal. And my other solution is also 0. And you might be like, how is that 0, Mr. Kelly? Like, how is that a solution? Because when I put a 1 in here, right, that makes that 0, which makes that 0, which makes that 0, right? Because it's the 0 product property. If I put in a 0 here, right, it doesn't matter what everything else is because you're doing 0 times something. So that's 0, which makes that 0, which makes that 0. So my two solutions are x equals 0 and x equals 1. I believe those are going to be my two inflection points, so we will double check that with the little sign chart here. If I plug in like a 5, I will get positive and a negative. If I plug in like a 0.5, I would get a negative here, and a negative here, which would make it a positive. And if I plug in like a negative 5, I'd get a negative here and a negative here, but that would make a positive. So it would be a negative and a positive, which would make that negative. Therefore, my two solutions are, I have an inflection point at x equals 0 and x equals 1.